Hello and welcome everyone officially to the FusionEPtalks. It's a student-led webinar platform for sharing knowledge about nuclear fusion, science and engineering. My name is Dhaval and I would like to introduce our speaker for today, Mr. Dieter Boeyaert. He's a returning speaker, so we are very glad and very fortunate to have such speakers who keep their faith in us and keep coming back. I'll quickly introduce Dieter to all our audience. After completing his M.Sc in mechanical engineering from the KU Leuven and Université catholique de Louvain, he started his PhD at the Forschungszentrum Jülich in the European CN collaboration framework of Eurofusion about power exhaust studies in the East Tokamak using neon seeding with SOLPS-ITER. After obtaining his PhD in 2021, Dieter joined the 3D PSI group of the University of Wisconsin-Madison as a postdoctoral researcher. In his work, the focus is on modeling of the edge of stellarators with EMC3-IRENE, and the main focus is on exploring the neutral exhaust in the Wendelstein 7X and designing a divertor for the HSX. So without further delay, I would like to welcome you all once again, and over to you, Dieter.
Okay, then I start sharing my screen. So I hope you can now all see my screen. So thanks a lot for the introduction. So I am going to talk today about the design of a diverter for HSX. And for the work that I'm presenting, I would like already first on this first slide to say many thanks to John Schmidt and Bob Davis, who are working together with me on this design, and from who I'm also showing some of the work in my slides. So when I'm talking about design of a diverter for HSX, especially when we talk about that in Europe, the first question is like, what is HSX? Which kind of device is that? And then afterwards, like, okay, when you start with designing a diverter, what are the options and how you make a decision how to go ahead with it. So that are also the first two things of which I will talk in my talk, which is first a small introduction to HSX, and then coming to which kind of diverter options you have in a stellarator. So when we look to HSX, what is HSX? HSX is an optimized stellarator. And for people who are not that familiar with stellarators, the question is then like, what do you mean with an optimized stellarator? With an optimized stellarator, we normally mean that we minimize basically the fraction of plasma particles which can escape from the confined plasma. And that we can do in different ways to optimize that. And most of the time, when you look to the field lines of such an optimized configuration, then we can distinguish different categories. And that you can see here on this picture on the right, which I took from the thesis of Matt Landerman. And when you look in the poloidal toroidal plane, then you can see that these lines are really straight going from top to bottom, or they are more like diagonal, or they are really going like from left to right, as what you also have in a Tokamak. And in this category, the most famous optimized stellarator is, of course, W7X. And that is what we call like a quasi-isodynamic stellarator. And HSX, about which I will talk today, is also optimized, but then slightly different. That is belonging to the quasi-helical symmetry stellarators. And that was basically the first stellarator they ever built, which was optimized. So, of course, from a theory viewpoint, there were already a lot of ideas from how can we optimize stellarators and what we can do from it. But HSX was the first one in which they proved that they can also actually build such configurations. And that immediately explains also the name of HSX, which is standing for the Helically Symmetric experiment. And it's located at the University of Wisconsin-Madison, which is in Wisconsin in the US. And in comparison with W7X, it's a rather small stellarator. So here on the right, you can see basically a comparison between HSX and W7X. And you can see that where W7X has a major radius of 5.5 meters, that HSX only has one of 1.2 meters. Also, when you look, for instance, to the pulse length, that is only 0.2 seconds in HSX, where in W7X, you can go even to 100 seconds. So there is a kind of a difference also in plasma volume. But with such kind of small stellarator, we can also explore what is possible. And especially HSX was mainly used to study core confinement, to see like how can we improve that confinement even further, and which kind of configurations can we get for that? Now, when I talk about installing a diverter in such a device, then the first question is like, yeah, what is happening currently? How do you currently have a kind of diverter in this device? And the answer is very easy. Currently, we don't have a diverter. That has to do with the limited heating power from HSX. So the heating power which is installed is only a few hundred kilowatts. And it's so low that, that there is no need for a diverter. Like currently, HSX is in operation for around more than 25 years. And now after these 25 years, you can start seeing on the vessel wall, like, where are the strike line locations? So that means for a couple of single of discharges, there is really no need to install a diverter. However, the current problem is that, the current interesting fact is that the ions are not heated that well. And for that, they are planning an upgrade to install an extra neutral beam injector. And when that extra neutral beam injector is there will be way more heat inside the plasma, which also has to come out. And then we will have the need for a diverter. And that's basically from where the exercise comes to see, like, how can we implement a diverter in our HSX Stellarator? Then the question is like, okay, installing a diverter, that's good to know, but what do we really want to achieve with a diverter and how we can go ahead with that? And for that, I would like to start basically from the definition of a diverter, or from the goals of a diverter from the ITER website. And there it is stated that the diverter extracts heat and ash produced by the fusion reaction. That basically means that we have to foresee a surface which can deal with the heat which is produced during our discharges in HSX. And at the same moment, we basically want to extract the neutrals, because our helium ash that are basically neutrals. So therefore, we are looking to how can we extract our neutrals out of our reactor. And for such a diverter that we use them for that, that will depend on the one side on the diverter geometry. So on the way how you place all the diverter plates and how you put that in a geometrical way over there. And on the other hand, it will also depend on the magnetic configuration that we use. When we look to this diverter geometry, you can say like we have open diverters and closed diverters. And to show you basically the difference between them, that you can see here on a picture from LHD, because in LHD originally they had a very open diverter. And then in a later stage, in the last phase of operation, they had a more closed diverter, which is here on the right. And in such a closed diverter, you basically find a way that you avoid that your neutrals can leak back into the plasma, so that you force your neutrals to be guided to the subdiverter. In that way, you increase then your pressure in the subdiverter. And then that's an advantage for pumping, because then you can pump out a higher fraction. That you can see here on the plot, here on the bottom. There you can see that here you have like a pressure of around 10 millipascal. And when they here introduce some extra structures with which they close the diverter, then you can see that that is 14 times more, and that you are up to 140 millipascals of pressure. Now, there are also disadvantages, of course, on such a closed diverter. And that's the magnetic freedom that you have. Like you can see here that we have here these extra structures like the dome and so on. That also means that you now have way less flexibility with your strike lines, because if you move your strike lines too far, it might be that you have already your strike point on the dome, or that it is not aligned exactly anymore. So that is a little bit a trade-off that you have to find between an open diverter and a closed diverter. So magnetic flexibility versus that you have a really good pump out of your neutrals. And that's, for instance, also the trade-off which was made when they decided how to build the current diverter of W7X. And there they said like, okay, we want to explore more magnetic configurations. And that was the reason why they chose for an open diverter. The second thing on what your diverter choice is depending, that is on the magnetic configuration that you have. So in W7X, we have what we call an island configuration. And in HSX, we have what we call a non-resonant configuration. And when you look to the magnetic footprint of that, you have here the two pictures on the right. And here you can see in W7X that you have here like a couple of big island structures, as we call them. And that means that if your particles escape from the core, that they probably will go through these small X points, and that most of your heat will be guided in that way, and that you can see easily where is located your strike line location. So that means in such an island diverter, you cut your island here, and then you know, okay, my island is cut the way where this border of my island is coming in contact with this diverter plate, that is the place where I have my, my strike line location. And that's the concept of an island divertor. But when we look to what we have here on the bottom, to HSX, there you don't see such big island structures, which you can cut then and get your strike line location. In HSX, you basically have not such resonant surfaces here, and that's also from where the name is coming. Like you have here a non-resonant edge, so a non-resonant configuration. And that means that the location of your strike lines will rather be defined by the bending of your magnetic curvature. So that means that at the locations where you make kind of a corner in your vessel structure, that basically is a location where your confined particles will easier escape from the confined plasma, and that are then the locations where you expect to have your strike lines. So we know now, like, okay, for HSX, what we want then to achieve? That is then we want to have such a non-resonant configuration, because to that we are bound a little bit, and we are aiming to have a closed diverter, as we want to see how well can we improve basically our neutral exhaust. And with that, we will start the study of exploring what can we do to design such a diverter then for HSX. Now, the first problem that we have with the current vessel of HSX is that in this vessel, there is no place to put a diverter. Like the confined region inside our lost closed flux surface is coming so close to the vessel wall that there is no space in between where we can say like, okay, we still develop a diverter structure. And therefore we decided that for this project in which we are looking to this HSX diverter upgrade, we only keep the coils of HSX. And for the rest, we start again from scratch. So that means that our first task will be like, okay, how can we design a vessel which is suitable for a diverter, in which there is enough space that we can put there some diverter plates. Once we have defined then a kind of vessel, then we can start about the next thing. And that is like, okay, where do we expect that we have diverter locations? That we do with field line tracing, which was originally also used, for instance, for the current W7X diverter. There they also did this with field line tracing. And with that, we can say like, okay, these are the regions where we expect that all our hot plasma will come in touch with our vessel wall. That's the place that we have to protect. So there, in front of that, we put diverter plates. Once we have defined these initial locations, then we can say like, okay, now we want to see how we can optimize it. And the two optimization criteria which we aim for in the end of our project, that's to minimize the peak heat loads, and then also to maximize the sub-diverter neutral pressure. So that are the final end goals, but so far we are not yet. So the first task is to say like, we want to design a vessel wall for HSX. How will we start for that? And for that, we started with on that topic, mainly John Schmidt was working. And for that, we start here from the last closed flux surface. And we say now, okay, at each location, we will have this last closed flux surface, and we try to, as we call it, lofting, so putting it a little bit more outside, and to see what is the farthest that we can go without having an intersection with the coil structures around. That we check for a lot of different toroidal angles, and then we can connect all these cross sections at toroidal angles, the surface that we have there for the maximum vessel, we connect them with each other, and then we have to do a final check like, okay, is this still fitting, this final structure fitting inside our coils? If yes, perfect, and that's what we obtain with here, the gray figure on the left, and then we can go further. Now, this is a maximum vessel that is ideal when you want to install something inside because you have a lot of space, but there is one big disadvantage of it, and that is like, we have still these coils from HSX around. We still have to fit this vessel somehow in the coil structure. And for that, this is of course more an advantage if we don't need all this space. So therefore, after lofting this vessel as far out as possible, we come to the next stage in which we say like, okay, now we check basically with field line tracing where we expect that our particles will travel inside our new vessel. And all the spaces where they don't come, where we don't find any particles, so that are mostly the spaces where you have a very short connection length, that we then can cut out again, because we don't need it anymore. And this makes it, from an engineering viewpoint, way more easy to install also actually this vessel inside the coils of HSX. If you want to know more about all the details, the numerical details of how this is done, there will soonish come out a paper of John in which he explains that more in detail. So we say now, like, okay, we have our vessel. Now we have to check what are the locations where we expect that we will have our strike lines. So the locations where we really put our divertor plates. And that we do with the field line follower flare. Flare, so, is a field line follower which is developed by Henke Frerichs at University of Wisconsin. And the first thing what we check with that is like, okay, we have different magnetic configurations. What is the effect of that on our strike line locations? So as I mentioned before, HSX was originally built to study core confinement. And that's still one of the things which is currently used. And for that, they say like, okay, we have our current standard configuration, as we call it. So the configuration in which HSX is running most of the time. But we still have some optimized configurations to suppress turbulence in the core. And these optimized configurations which suppress turbulence in the core, they are more elongated. And then we want to say like, okay, what is the difference between the two when it comes to strike line locations? Because if we install a diverter, we want to be sure that is it suitable for both of them. And that's the difference that you can see on this slide. So here on the left, you can see which strike lines we obtain in the toroidal and poloidal angle frame if we use the current standard configuration of HSX. But if we say like, okay, let's now use this optimized configuration for turbulence, then we come here in the plot on the right. And you can see that that makes a difference. Like here, our strike line locations are way more narrow than what you have over there. But we can also see that the location where we have the strike line locations still stay very similar to each other. Like it's still around the line, you have like, you can see here 4 lines, and it's always around these 4 lines. So that's something that is important to keep in mind. Like, okay, if we base it on this, these locations will be correct, but we have always to make sure that also our diverter plates would be wide enough that they are suitable for both locations and for both configurations. Now, the next thing is that if we have our diverter, or if we are really running our stellarator, we also expect that we will have different discharges with different temperatures. Like you will have attached discharges and you will have detached discharges. That means that in both of these discharges, our electron temperature at our diverter targets will be different. And in flare, the diffusion coefficient, which is expressed over there, is not fully a diffusion coefficient, or yeah, it is the normal diffusion coefficient divided by the velocity of your particles. And this allows us to also check what would be the influence of different temperatures. So for our diffusion coefficient itself, so the D that we have here on the top, for that we always assumed in the presented studies that we have 1 meter square per second. But for the velocity, which we have here on the bottom, that is depending on the electron temperature that we have over there. And with that, we can vary the electron temperature. For I did here a study from 5 electron volt until 15 electron volts. But in the final design studies, we also went up to 50 electron volts to really try to have the entire spectra of what is possible and if we cover everything. And also here you can see that the locations, the main locations are similar to each other, but that there are again small differences between running here with smaller diffusion, and so with a lower temperature, and here running with, wait, that I mixed up. So here running with a higher diffusion, so meaning with a lower temperature, or here running with a lower diffusion, so meaning with a higher temperature. So when we take this into account and we say like, okay, we start now with looking in 3D where we have these locations that you can see here on the plot here on the bottom. Here you can see in yellow, you have the last closed flux surface. And in blue, you have our vessel wall. And then you can see that you have here like the different strike lines, which are indeed at the locations where you have the strongest bending. As I explained before, that's what we expect for a non-resonant diverter, and that you can see here too. Now, this was only an example for one diffusion coefficient and one magnetic configuration. When we check this for different diffusion coefficients and we do this more elaborate study, then we come to a design as what you have here. And from that, we have a very small video that you can see it well in 3D. And here we have like our diverter locations determined for the first time. So you can see here in the middle, you have your last closed flux surface. So that's basically the last closed flux surface that we get from VMAC. And then you have here in these different colors, you have all the divertor locations which came out, where there will be some strike lines touching the targets, touching the wall. So in front of that, we said like, okay, 2 centimeters from wall, we place here these initial divertor targets, and with that we can work further. So the next question is then like, okay, we have now our initial locations of our divertors. Now we want to see how we can optimize it further. And for that, we have some extra tools that we use for it. That is EMC3-Lite and EMC3-EIRENE. So EMC3-Lite is mainly used to optimize the divertor shape to minimize the peak heat loads. Why we use EMC3-Lite for it? Because it's a super fast code, like it runs within several seconds. And then we can see like, okay, what is the effect of changing a little bit the shape of the diverter on what we get in the end. And on that, Bob is working a lot. So he might in the future present way more results on that. And he could show that basically when we start from our initial design that we had obtained with field line tracing, that 95% of the heat will still be deposited on the proposed targets structures. And that basically shows that we get a very similar result with this, or with this field line tracer and with this initial EMC3-Lite simulations. And now these EMC3-Lite simulations will then be used as a starting point to see how we can really shape our diverter further to optimize this for heat deposition. But that's still something on which we are working. So that's work for the future. The same is for the EMC3-EIRENE simulations. So they are mainly meant to optimize in a later stage, not only for optimal heat exhaust, but then also to see for the neutral exhaust. And therefore here a simulation is made in which you can see the entire vessel wall. So this is still a simulation without a diverter structure included. And here we go all the time around. This is plotted a little bit differently. So here you can also still see on the x-axis the toroidal angle, but on the y-axis you can we go in centimeters around the entire vessel wall. And then you can see that we have also similar strike line locations as what Bob obtained in his EMC3-Lite simulations. And this is then our starting point to say like, okay, if we change now something on the shape, what will be the effect on our neutral pressure and in that way on our possible neutral exhaust? With that is all still work in future. So that's just something, the first glimpse of this study that I would like, that I wanted to share with you. So with that, I come to my summary of what I have presented to you today and what are the next steps on which we are working. So I presented to you that HSX is an optimized stellarator. More precisely, it's a quasi-helically symmetric optimized stellarator. It is a small scale in comparison with W7X. In the current vessel design, there is no space for a diverter, and therefore we require a new vessel and a new diverter in order to increase the heating power. For the vessel design that we generated using field line tracing and some MATLAB tools that John Schmidt developed, we have then determined the initial diverter locations, and now we are working then on the optimization of this diverter shape to see how we can minimize the peak heat loads and how we can maximize the subdiverter neutral pressure. And with that, I would like to thank you for your attention. And if you have questions, I will try to answer them.
Thank you so very much, Dieter, for the impeccable timing and at the same time, very insightful talk. I will now open the session for questions and answers.
Yeah, hi Dieter. Thanks for the overview. Also really cool now to see, and I love the video where you can see the possible diverter locations. That's really neat. I really like that. What I was wondering at HSX, and I guess we briefly talked about it, your plasma, your pulse length is pretty short, and your neutral dynamics need, I guess, well, my question is, what kind of timescale of a discharge length are you looking for to then eventually experimentally validate your neutral pressures?
So at the moment, indeed, we only have a pulse length of 0.2 seconds, but we are aiming to increase that up to 1 second to make it possible to study the neutral behavior, because you're indeed right that when we stick to the current discharge length, then we cannot look to the neutral dynamics. And as we also want to check, as I mentioned, also we want to check detachment studies. When we only have a pulse length of 0.2 seconds, that's also not possible. So therefore, we are at the same time as this is part of a major upgrade in which not only the divertor is included, but in which also a lot of the other systems are updated. One of the other things that we are aiming for is then to increase this pulse length from 0.2 seconds to 1 second, that we can also study that further.
I would have a second question, but if there are others, I would just go back to the queue.
But I think you can go ahead.
Okay. Regarding your design cycle, so on the last slide, so you're planning to, I guess, because you're an expert in it, using EMC3-EIRENE or EMC3-Lite for the peak heat loads, yeah, and then EIRENE for the neutral pressures. What do you expect for design cycle? How long do you think you'll need from coming up? Because I guess you now have from John like this geometry where in theory you can put targets. What do you expect going from a model where you have a target in there to the result of like sub-divertor neutral pressure?
So the thing is, so Bob is now working with EMC3-Lite and I'm focusing on EMC3-EIRENE. The thing is, we are also trying to find a way to do this in a kind of structured way. So not that we are doing randomly changing some of the target profiles and then checking what is happening and then do again a simulation and then changing it further. We are trying to have an optimization algorithm behind it. And on that we are now working. And I think that that will basically determine how long it will take. That will be easier for EMC3-Lite than for EMC3-EIRENE, as EMC3-Lite is running way faster and is also easier to make changes on than EMC3-EIRENE. So I find it at the moment kind of difficult to really predict. Like the example to which I can look from the past is what they did for LHD. And in LHD, it's basically if you have an initial design. So let's say, for instance, that we find a design which is optimized for minimal peak heat loads in the not too far future. Then I speak about several months. Then afterwards, it will be like, okay, if we have this design, we know how it looks like. Then you can see, like, for instance, this dome structure as they had at LHD, still extra baffles that we can build in and to check what is the effect of that. There, the main question will be like, how much space do we have to put all these extra components? Because when you look, for instance, at LHD, there they have really long legs, which are going really far away. That space we will not have in HSX. So there we will also be kind of limited. But it's difficult to predict at the moment how long it will exactly take. But I expect that it will take several months before we have an optimized diverter for peak heat loads, or at least the first idea about how that can be exactly minimized. And then in the next step, we will go ahead with this EMC3-EIRENE and checking if we put baffle plates and so on, what is the effect of that?
Yeah, modeling takes time.
Unfortunately, yes.
Thanks.
Thank you very much for your question, Thierry. It's really nice to see fellow speakers also collaborating, because we just had Bob Davies presenting his work a few weeks ago. Right, looks like there are no more questions. So I'd like to take the opportunity to thank Dieter for the wonderful talk, very insightful talk. And also for everyone for joining us. That's it for today. Thank you so very much, everyone, for joining. We will keep looking forward to seeing you in the audience, and if you are interested also as a speaker. But till next time, it has been a pleasure. Thank you so very much, everyone.